The second version of multiplication of vectors is the so-called cross product. Now, the definition of cross product is a lot more complicated than dot product. Now, this only works in 3D. That means, in particular, it doesn't work for 2D vectors. It doesn't work in any dimension higher than 3D. This is only specifically for 3D vectors. Now, before we get to cross product, we need to talk about the basics of something called the determinant. And the determinant applies to square matrices, and we'll start out with the small case. If we have just a number, so if we have a 1 by 1 matrix, if we take the determinant of this matrix, we get just the number itself. Not too complicated so far. If we look at a 2 by 2 matrix, A, B, C, D. Now, the way we get this is we're going to expand along the first row. So what I mean by that is that we're going to start out with the A, that gets a positive sign. Then we're going to move on to the B, which gets a negative. So first up we have an A. Now to get what A is multiplied by, it's going to be multiplied by a smaller determinant. And to figure out what goes in this determinant, we cover everything in the same row and column as the A. So if we cover everything in the same row or column as the A, the only thing left over is the D. So the D is what goes in this determinant. That's our first term. Next up, we're going to subtract B times a determinant. And to figure out the determinant that goes in here, we're going to cover everything in the same row or column as the B. So we cover the row with the B, we cover the column with the B. The only thing left over in here is C. And remember, the determinant of a number is just the number itself. So this gives us AD minus BC. For a 2 by 2, you can think of this as sort of a cross multiplication. A times D minus B times C. So we cross multiply those to get our determinant. Now we're going to look at a 3 by 3 case, which is where we really want to stay. If we take the determinant of the matrix ABC, DEF, GHI. Now to expand this determinant, we're going to go along the first row again. These signs alternate, so the first one is plus, then minus, then plus. So first up we have A times a determinant. Now this determinant will be a 2 by 2. The original matrix was 3 by 3. The smaller matrices are always one dimension less. So we're going to cover everything in the same row or column as the A. And if we look at what's left over, that would be this 2 by 2 matrix, EFHI. So EFHI is our 2 by 2. That takes care of the first term. The A is now done. Now we're going to subtract B times a determinant. And this determinant, the matrix that we get for this, we're going to cover the row and column containing the B. So we cover everything in the same row as B, everything in the same column as B. The only stuff left over is D, F, G, I. D, F, G, and I. Plus, so we've done the A, we've done the B, now we move on to the C. The C is positive, so we've got a plus sign. C times a determinant of a 2 by 2. And now this 2 by 2, we're going to figure out the 2 by 2 by covering the row and column containing the C. So we see that the only stuff left over is D, E, G, H. That's going to be our 2 by 2, D, E, G, H. So we took this 3 by 3 matrix and it reduced to a set of 3 2 by 2 matrices. And then each of these 2 by 2s, we can do our little cross multiply trick. So this 2 by 2 here is EI minus FH. This 2 by 2 is DI minus FG. And then this 2 by 2 is DH minus EG. So that would be, once you distribute this all through, we're going to have 6 terms in here, and that gives us the determinant of this 3 by 3 matrix. So now, to get onto the idea of cross products, a cross product is a special type of determinant. So if we've got two vectors, let's say we've got U as U1, U2, U3, and V as V1, V2, V3, The definition of the cross product of these two vectors is the determinant of a special type of matrix. The top row are the standard unit vectors, I, j, and k. The second row are the components of the first vector, so u1, u2, u3. And the third row are the components of the second vector, v1, v2, v3. And we expand this determinant out using the rules that we just established in the previous step. Let's do a concrete example of this. Let's say we wanted to take the vector 1, 2, 3 and cross it with 2, negative 1, 4. So what we do this is we expand out this determinant. The first row is I, j, k. The second row gives us as our first vector 1, 2, 3. And the bottom row is the second vector, 2, negative 1, 4. Now to expand this determinant out, we're going to start with the top row. And remember the signs alternate, plus, minus, plus. So we start out with I times the determinant of a 2 by 2. And the 2 by 2 is determined by taking the I, covering it up, and everything in the same row or column as the I. So the only stuff left over is 2, 3, negative 1, 4. That's what will go in this 2 by 2. 2, 3, negative 1, 4. So that's the I. Next up comes a j, and it's negative because this alternates, times the determinant of a 2 by 2. And we determine this 2 by 2 by covering everything in the same row or column as the j, which leaves us 1, 3, 2, 4. 1, 3, 2, 4. So we've dealt with the I, we've dealt with a j, then we move on to the k. That one's positive, times the determinant of another 2 by 2. We get this by covering everything in the same row or column as the k, which leaves us with 1, 2, 2, negative 1. Okay, now each of these subdeterminants we can compute by doing that little cross multiply trick. So this gives us 8 minus negative 3. And then for the j component, 4 and 6. So 4 subtract 6. And then for the k coordinate, we're going to cross multiply again here. So negative 1 subtract 2 times 2 is 4. Okay, and then we can finally simplify these. So this is giving us 11 in the I component. 4 minus 6 is negative 2. With that negative sign, it'll give us positive 2j. And then in the k coordinate, we combine those and we get 5k, which we could write in component form as 11 to negative 5. So that's the cross product of these two vectors. Now once we have the definition of cross product, there are a few properties that cross product has that we're going to find useful. So the first one up is orthogonality. And that is if you take u cross v, this is perpendicular to both u and v. So if you're looking to find a vector that's perpendicular to two vectors, you could set up a system of equations involving dot products, or you could just cross the two, and that solves, that sort of kills two birds with one stone and allows you to solve both problems at the same time. We also have an angle property for this. If you recall, we had a version involving dot product where we knew that the cosine of the angle was u dot v divided by their lengths. We have a similar property for the angle involving cross product, and that's the sine of theta is going to be u cross v divided by length of u, length of v. However, you got to be careful because u cross v is a vector. We cross product of those two and we get a vector perpendicular to the original two. We've got to take the magnitude of this cross product. So we take the magnitude of the cross product divided by the magnitude of each individual vector. That gives us the sine of the angle. Okay, and finally, we've got a triple product, and this involves actually finding the volume. This will be important when we get to integration down the line. The volume of a parallel pipette. I may be spelling that wrong, but hopefully that's the right idea. Parallel pipette is kind of like a box, although the sides of the box don't need to be rectangular. So this forms a parallelogram. And then if I take some third vector that say comes out of the plane, I'm getting this box. And this box is called a parallelepiped. It's not necessarily rectangular. None of the angles need to be right angles. If I want to get the volume of this, what this is, if I've got vectors u, v, and w, the volume of the parallelepiped, what I can do is I can take two of the vectors and cross them. So I can take u cross v, and then dot that answer with the third vector. Now, depending on the order I take these, I may wind up with a negative number. So we take the absolute value of this, and this will give us the volume of the parallelepiped whose edges are determined by u, v, and w. Okay, there's one more property that's sort of inherent in this, is that if I switch the order on a cross product, if I take v cross u, this is the negative of u cross v. And this is actually a subtle property that determinants have, where that we'll get into when we get to those by in the linear algebra section by the end of week 6. So as far as physical applications go, the only physical application we'll touch on is that of torque, or if you look at this in general, moments. And this, if you take statics at some point, is going to be kind of a big deal. Statics. So the idea of torque is we have some kind of pivot here, and then we have a lever arm based on that pivot. And what we want to do is we want to turn this lever arm around the pivot, and we want to know sort of the strength of that turn. So we have a position vector for indicating the think of this as sort of like the distance that we are from the point of pivot, and then we've got a force that's applying to the end of the bar. Now, if this force is perpendicular, then we're sort of maximizing the amount of torque we're getting. We're getting the most turn we can possibly get. So that tells us that the torque will be maximized when the force is as close to perpendicular as possible. If I were to take that force and maybe induce it at an angle, I'm going to still be turning it, but not quite as powerfully as if we were pushing straight perpendicular. And sort of the worst scenario of all is if I push straight on that lever arm, I'm not turning it at all. So and that's indicated by having zero torque on there. So if we take R cross F, this is giving us torque. And if you just look at our the sign property that we had right here, we can see that if we want to sort of maximize the cross product, that's going to be when this is as large as possible, and that happens when the angle is a right angle at pi over 2. So if we want to maximize the torque, if we want to maximize the cross product, the angle will have to be pi over 2. If you want to have no torque at all, if you want the cross product to be 0, then we want the angle to be 0, which means they're running actually in the same or opposite directions. So we'll have a chance to investigate cross product and some of its properties in subsequent videos.